Hey everyone, in this video I want to show you how to go about finding your uncertainties in your measurements in this lab. You will be using this throughout your semester, so I'm going to make a separate video for this one. In order for you to estimate the uncertainties in your measurements, we want to first learn about the concept of our normal distribution or a Gaussian distribution. As you can see, that it looks like a bell curve like this. So let me give you a quick example of what it looks like. Let's say that I have our assignment that I'm going to give to you, and then I estimate that average time that you're going to finish your assignment is about 16 minutes. So the x-axis here is time, which the average is 16 minutes. And then the y-axis here is number of students that fall into the time range, and this is a histogram. So that let's say in 50 minutes, and then I have this many students, which is like 70 minutes. I have this many students finish in this time range, and then as you go further away from your average, you're going to have less students finish in this time range. And then let's say I have just this many students finish in like from 30 to 40, I have like this many students, and then from 40 to 50, I have this many students, and so on. So that this is about 90 minutes. So if I take, actually there's a formula for this. If I use this formula, say that, let's say I have like for example, student finish at 55 minutes, then that's xi equals 55, and then I just sum up xi for every single student and divide by the sum of all the students. So it's sum of the number of all the students, and then I say that my average x bar, or the mean, is equals to 60 minutes, which is my average. And then there's also, you can also calculate the standard deviation of your this set of measurements, and then so xi is a time of the student that it finished for each student minus the mean, which is 60 minutes. And then if you do that for every student and square it, sum it up, divide by a total number of students minus 1, and square that, you're going to get this, the error, or this is also called the standard deviation. Well, there's different way you're writing this. I can write it this or write it like that, but I'm just going to tell you that my standard deviation, let's just say it's like 50 minutes, sorry, not 50 minutes, let's just say 10 minutes. So that it's actually, then for this particular measurements of this class, I'll say that I have like about 60 students in this particular class, 6 students. So that you're going to expect, if I give you this number, the mean 60 and the standard deviation equals 10, so that you're going to expect, which is in here, 68%, between 50 to 70 minutes, you're going to have 68% of students are going to lie within this time range, which if you want to calculate is 60 of total number of students times 68, 0.68 equals, I have a calculator, let me calculate that, which is about 40. So you're going to have 40 of your student that is going to lie in this range. Well, it doesn't, this shape doesn't look so well. I guess this one should be much lower, but you're going to expect that 40 of your students is going to finish this assignment between 50 to 70 minutes. And then if you're 2 standard deviations away, which is 60 times 95, 0.95 is going to equals to, let's do the calculation. So it's about 57 students are expected to finish between 2 standard deviations away, which is 40 to 80. So you're going to expect 40 to 57 students to finish assignment in this time range, and then the other 3 students are going to finish between before 40 and above 80. So that's how you calculate that. And this is called normal distribution or Gaussian distribution, which for most of the time it's actually hold pretty well. Like for example, I measure our like my keyboard, for example, is 0.5 meters, and then if I measure this thing, use a ruler 10 times, I'm going to have something. It's not going to be exactly like 0.5. It's going to be 0.51 sometimes, or like 49 sometimes. It's going to be around this time, like around this, but it's not going to be not exact if you have different people measuring this. So that if you take the average and then take the standard deviation, that is what you are going to report. Like in this case, it's 60 plus minus 10. And how you calculate this 60 is that you use this formula and that formula. And this formula is calculating your standard deviation. Let me just show you how do you go about doing this in our Excel sheet. Okay, content. So let's say I want to measure something that is about 10 centimeters. And then I have 10 different students using a very good instrument to measure this thing 10 times. And in Excel, you can first just go equals average and put a bracket there. Select all 10 different measurements and then put another bracket. Okay, let's put it a different place. So equals average, and then select all this, hit enter, then this is the average of all the measurements. Then we want to calculate the standard deviation, which you need to use this formula, but in Excel it has a formula and you don't have to input it manually. You just input equals STDEV bracket of this bracket, and then now this is your standard deviation, this is your average. How you go about reporting this number is, first of all, you want to round your error to only one significant digit. In this case, it's going to be 1. And then once you have your error, then you want to round your number to match the last digit, which in this case it has to be like here. So now what you're going to report, your measurement is actually going to be 10 plus minus 1. So 10 is your mean, 1 is your ST standard deviation, STD DEV. This is what you're going to be reporting. And it is important that for your error in this lab, you want to report only one significant digit. And then for your value, the number, you want to report the digit that is matching your last digit of your significant figure of your error. So in an actual experiment, then there might be a question asking you, is your measured value matching the theoretical value? How do you go about that? So you can actually, let's just give an example. So let's say I have measured 10 plus minus 2, and then it looked like, let's say 10, and then this is 8, this is 12, and then I have 6 and 14. If this matching a normal distribution, the thing should look something like that, right? And then if your theoretical value is, let's actually go here. This is the lab manual. If you go up, and go to section 4.3.4, in here it actually tells you the wording. How do you go about this? Let's say the theoretical value is 10. Then, well, 10 plus minus 2, well, that's matching very, like, if it's 10, then it's matching very well because it's 10 plus minus 2, and it's right at the middle. Then that is very good, right? And then if it's 9, then, well, 9 is here, and then it's within 1 standard deviation or errors away. Well, we can say that it is still quite close to the actual our measurements, and then if it's within 1 standard deviation away, that is with above 8, below 12, then we say that it's a good agreement. And then if it is 7, the 7 is here. So it is above 1 standard deviations away, but it's not further away until 2 standard deviations away. So that in this case, we say that there is a modest agreement. So you see that it's still a chance that this is agree with that, giving the spread of your error. So another thing I forget to mention is that so this standard deviation is actually a measurement of the spread of your data. If you have, like, if there's students that spread to a very large range, then this standard deviation is going to be large. If it's very narrow, that like everybody is finished right on time about 60 minutes, then this standard deviation is actually going to be small. So this standard deviation of the error is actually a measure of the spread of your data. So that if it's within 2 standard deviations, but above 1 standard deviation, we say it's a modest agreement. And then if it's like after 3 standard deviations away, which is like this range or like that range, then we say that it's very unlikely that our measurement is matching the theory. So that we say that there's a poor agreement between the theory and the experimental result. So you can just look at this portion of the lab report and make your wording to be similar to this, and then that's how you go about compare experimental value with your theoretical value. So let's go back here. If we come here, then in this one, you probably have already learned this in your high school. You have 4 single digits for the first one. For this one, you have 6 single digits because you have a 0, 0. It doesn't matter it's a 0, 1 or 0, 5. As long as you have something here, it counts towards your single digit. In this one, you have only 2 single digits because anything before the 4 doesn't count towards your single digit. In this one, all those numbers count towards your single digit because you have a 1 in the end. And this one you have 3, and this one you have only 1 because you don't have a dot here. If you have a dot here, then like this one, all those towards your single digit. And this one has 6 single digit. You should learn this in high school. But the thing in this lab is that your error or your standard deviation, your error should have only 1 single digit, and for your measurement, it should match your error should match the last digit of your actual measurements. So that's that part, and let's then the difficult part is actually how to do error propagation. Let me so there are different ways to do error propagation. The way that you should be doing is using a master formula in this way. You're expected to know derivative by now, so that the derivative of x to the power n is equals to you put the n to the front, x to the n minus 1, and then you should already know that. And then for log x, then it's x over 1. The derivative of that dx, this thing dx is equal to that. And then you should already know that. And then e to the x, things like this, you should know this. And then sine x is equals to cos x. I forget, you have probably, and then the x of cos x equals sin x. I forget which one you have. You have minus sin. Let me just look it up real quick. Yeah, so that's all right. You have a minus sign in this one. And then, so if you do our errors, then you need to do about partial derivatives. And partial derivative is actually not that difficult if you know how to do derivatives. Let's say I have x times y, and then I want to, for partial derivative, is actually this simple. Let's say just dx and then this one. Now this y, if you're doing partial derivative, this y is just a constant. It's just equals to, if you don't have this y, then the dx is just going to 1. It's going to 1 times y, which is just equals to 1. Sorry, what I mean is equal to y. And then it's same story for if you're doing partial derivative of x plus y. It's the same story. Then it's 1 again. But for this case, because y, we just imagine it as a constant. So the derivative of a constant is 0. So it's actually 1 in this case. I don't know what else to tell. It's just that simple. You just for any variable that is not the one that you're doing, you treat it as a constant. That's just how simple that is. So let's do some. Then in order for you to find your uncertainties, you use this master equation. So you have to use partial derivatives. For example, let me just apply those different things. For example, this x, let me just apply this one using the master formula here to apply to this one. So we already know that the f x is 1. So this one equals to 1, and then this error of x squared plus, it's 1 again, error of y squared. So that's it. So for this particular one, it's just equal to that, because when you did this one, data x is just equal to 1. That's how it is. And then for this one, for example, x times y, then the f x is equals to y squared, and then error of x squared plus, and then this thing y is going to equal to x squared, and then error of y squared, all that thing. And then it's different from this one, so that you can actually do something about this. For example, you can do y squared over x squared times x squared times y squared, and so I just have our like x squared divided x squared, that's just going to be 1. It's the same thing. A of x bracket square plus, and then x squared y squared divided by y squared, because that's 1, it's just x squared. A of y or bracket squared. Now we can just pull the x squared and y squared out. X, y divided by a of x divided by x all squared plus a of y divided by y all squared. So it's like that. You see, you can just use this, you can apply master formula to this one in order to get that. And well, this one is sim x to the y divided by y in the denominator just equals y to the minus 1. So why don't we do this one? X to the power of a and y to the power of b. Why don't we take this one, apply master equation to this one, so that x to this one is going to equals to a x to the power of a minus 1 y to the power of b bracket squared, and then a of x squared plus same thing to the y. Whoops. It's b x to the power a y to the power b minus 1 all bracket, making things smaller, and then a of y squared. Then if you just do the trick, and it's just a squared x to the power a y to the power b a of x divided by x bracket squared, and this thing is also bracket squared, right? Plus b squared x to the power a y to the power b bracket squared a of y divided by y, because I times this by y, I have divided it by y so that it is fair. And then you can just, I guess you cannot pull an a and b, but you can pull the x to the power a and y to the power b out, and then everything a squared, and then a of x divided by x squared plus b squared a of y divided by y. So like that, and then so that's how you get that one. It's that you apply, you have the delta x, apply delta x to the f. So it's that our so this is the first way you do, is that you actually apply the master equation. There's actually a simpler way to do this, is that you actually apply this table. Of course, is a master equation. You can use master equation on anything to get what you want. But using this table with a chain rule actually works pretty good. So let me make up some examples and show you. Well, the video has been 20 minutes. You might want to get a drink, but here is one example. This is my favorite one. You probably have already noticed this is a formula for gravity. So this g is a constant, and we are not expecting to have any air in this g, so it's a constant. So when you're doing for a constant, you have air in big M, you have air in small m, and you also have air in R measurements. And for g, there's no air in that. So when you're finding the air for this f, you forget about the g. You just put the g in the front and just carry it with you. Now it's equals to m r to the power minus 2, right? Because it's in the denominator. Anything in the denominator is equals to that's into the power of minus of that. If it's just divided by r, then it's r to the minus 1, but it's divided by r squared, so it's times r to the minus r. So now we can actually use this formula right here. So that because g is a constant, you just leave whatever g out, and then you just m r to the minus 2, just write like that, and then square root of a is the power, which the power of m is 1, so that area of big M divided by big M part squared. A in this case is 1, and then plus small m, area of small m power squared, plus, and then this is r to the power 2. Well, so that's minus 2 squared. Oops. Minus 2 squared times r squared. So that's it. So the area of f is just simply equal to this chunk. You see how I did with the minus 2? I just put the minus 2 to the front, and then it's like that. So this is similar to because you already know this. I derived that from the master formula. So you can take this as a result. Just use it. So this is a table. You can just apply this to things like this, and you just have to rearrange it to the right form. And then now, if for example in your question, then it's probably going to tell you m equals, let's say 10, and then area of m equals like 2, and then small m equals to 5, area of small m equals to 1, some things like that. Then what you do is you plug in all those numbers, then plug in a g, then you're going to calculate the area of f, and then what you f is going to be f plus minus area of f, and that is what you're going to be getting for that kind of question. And then that's like a good way of calculating the error. Or if you have a table like that, because I like this way, it's simple, and then you don't have to do partial derivatives. You just apply a table. Let me give you another example to this. Okay, this is another example. So we know x equals 10, and area of x equals to 2, and y equals to 6, area of y equals to 3. Okay, and then a is a constant, equals to 25, and b is another constant, equals 20. So that then what we're finding is the area of z, and then, well, it's not an easy question, but let's just do it. So we're going to using a chain rule, which is my favorite in this class. So w equals to x squared plus b times y. Now z equals to a times w to the power of half, right? So w is just that. Now so the area of w equals to, well, it's area of this one plus area of that one, so that you have to, okay, which formula do you use? So it's area of, so we're going to use this formula, okay? Area of x squared all square plus area of by all squared. Now it's a little bit tricky because area of x squared, we'll have to use this formula, x. So it's x squared, 2x area of x. So area of it's 2x area of x all squared. So it's a little bit tricky because it's like that. And then plus area of by, because area of y is just going to be where b times area of y. Your area of y equals area of y, I guess. And then b, the constant, you carry that thing with you. So it's area of w is equal to 2x area of x squared plus b times area of y. Ooh, okay, so that's that. Now we're going to figure out what is area of z equals to a. Well, okay, so w to the power of a half. Let's look at this one. X to the power n, and we can see that takes the n out. A half times w to the power of a half minus 1, and then area of w, right? Which is equal to a half area minus a half area of w. A times a half times that, and then equals to a times a half, because it is power a half, so it is in the denominator. And we can just rearrange for this. We put a here on the top, area of w here, and then 2 is here, and then omega to the half is just equals square root of that. So it's like that. If we don't have this a, then we can just forget about this a. The area of w to the half is equals to area of this square root of that, like this. Well, this 2 is coming from because this you have x to the power of n, and then it's x to the power of a half, and then this n is brought to the front, and then a half minus 1. It's like a half to the brought to the front and a half minus 1. Then that's where this thing came from. So it's like that. Now we know w, we know area of w. What we need to do is just plug in numbers. It's kind of a hard example. I should probably use an easier example. But here is what it is. 2x area of x, which is just that one, plug in here, plus, you see those kind of things are not actually hard. You just have to like do it step by step. Square root of w is equals to x squared plus by. Yes, so this is the final result for this problem, which is a little complex, but you see, you just follow the steps, and then it's not that. Let me give you another example, which is a little bit easier than this one. Okay, so let's do this example. So for example we had before, because I already told you the number for this, all you calculate this value is that you plug in all those different numbers into this and then do the calculation, which is not easy, but it's tedious, but not hard. And then let's do this one. So we're going to actually let's call this thing z. We're going to use a substitution, which we say that w equals to x squared plus y, and then for the z equals to b log w. Simple as that. And then we use this formula here so that z a of z is equals to b w absolute sign and the a of w. And then that's a of w is easy enough. The a of this plus that, use this formula, a of x squared plus a of y. That's just simply equals to 2x a of x all squared plus a of y all squared. And then a of z equals to b times, so this b is actually not in denominator, it's before that. So you see that for every constant I'm doing, I'm not doing anything with the constant, just put it in the front and then just leave it there like that. And then a of w is this chunk, square plus a of y squared all divided by w, x squared plus y, and then I'm supposed to sum that. So that's it. Simple as that. So I have in this video covered two ways of doing derivatives. The first way is you can do it using the master formula, which you can apply partial derivatives when you just assume other variables to be constant. When you're doing for x, for example, then you assume y to be constant. And then you can also use those different formulas as I showed you in this example, so that you can, for complex problem like that, you can use a substitution. I don't think you will meet any harder problem. I don't think you're going to need any other tools than this. If you do, and then I will tell you what you need. But this is how you're going to do, how you're going to find uncertainties for different formulas. So I hope you have learned all of this, and if you want another practice problem, you can send me an email. I can give you different practice problem and give you the answer to it. Then that way should be the best way to learn. If you want that, just send me an email, and I hope you have learned everything I teach you in this video, and I will see you in my class. Bye now.